commercial green laser pointer, as shown in the figure below, supplies an output power of 5 milliwatts at a wavelength of 532 nanometers. The light is contained in a circular spot whose radius is 1 millimeter. In Part A, we're asked for the frequency of the light, and we recognize that for any wave, the velocity of that wave is 1 wavelength per period, or lambda times f. Solving this expression for the frequency, we recognize that if we put in the velocity of light, 3 times 10 to the 8 meter per second, and the 532 nanometers, where nano is 10 to the minus 9, we'll get a frequency of 5.64 times 10 to the 14 hertz. In Part B of this problem, we are asked for the intensity of the light in watts per meter squared. The intensity of the light has to do with the fact that light waves deliver energy from one place to another, and to remind ourselves of the formulas that apply, I always like to begin with the energy density of any electromagnetic field, and energy density will of course be in the units of joules per cubic meter. Early on in the class, we derived the fact that anytime you have an electric field, such as inside a capacitor, you have an energy density of 1/2 epsilon naught times the strength of the electric field squared, and anytime you have a magnetic field, you have an energy density in joules per cubic meter of magnetic field squared divided by mu naught. Electromagnetic waves themselves are self-supporting in that the varying electric field generates the magnetic field, and the varying magnetic field generates the electric field. Therefore, the strengths of these two terms are linked to one another. As it turns out, the electric field carries half the energy, the magnetic field carries the other half, and so this expression can either be written as twice the first term or as twice the second term. This is all fine and good for energy density, but we are actually hoping to solve for another quantity, which is intensity, and the units on intensity are watts per square meter. We can deduce the relationship between these two simply by a dimensional analysis. We note that a watt is a joule per second, therefore we're going to need to introduce a dimension of 1/seconds in order to get the appropriate expression, and since the right-hand side has per square meter and the left-hand side has per cubic meter, we need to introduce the dimension of meter. If we ask ourselves for an electromagnetic wave, what is the amount of the meter per second? Well, that's the speed of light. And so we recognize that the energy density times the speed of light is going to equal the intensity for any electromagnetic wave. Although this formula will be critical in a moment, it is actually not necessary for the solution of Part B. In Part B, we're asked how many watts per square meter, and we're told that the laser produces 5 milliwatts, and it does so in a circular spot whose radius is 1 millimeter. Therefore, the area over which this light exists is pi r squared. Plugging in the numbers, we come up with 1592 watts per meter squared. In order to solve for the energy density, we're going to make use of one of the formulas that we derived previously that relates the energy density to the intensity, which can be solved for the energy density as intensity divided by the speed of light. Plugging in the result from Part B, we'll get an answer of 5.31 times 10 to the minus 6 joules per cubic meter. Finally, the last two parts of this problem ask us for the RMS values of the electric and magnetic fields. The expressions that we're going to use are the ones we derived previously, wherein we know that for any electromagnetic wave, the total energy density is twice the contribution of the electric field alone. Clearly, as the electric field varies from peak to trough and goes through zero, the energy density of this wave also varies, so we can consider this expression in more detail as being an average energy density, which is related to the average electric field squared. Therefore, we can solve for the average electric field squared and take the square root, and we immediately recognize that this expression is the RMS value of the electric field. And according to the previous calculation, it's equal to the average energy density divided by epsilon naught. And so using our result of 5.31 10 to the minus 6 from the previous part of the problem, we're able to solve for the RMS electric field produced by this particular laser to be 774 volt per meter. Finally, we need to move forward and calculate the RMS magnetic field produced by these electromagnetic waves, and we recognize that in any electromagnetic wave, because the electric and magnetic fields are self-supporting of one another, they cannot occur in an arbitrary ratio. In particular, we learned that the electric field is equal to the speed of light times the magnetic field. Students often have trouble remembering this formula, and there's an easy way to help. Recognize that a magnetic field of 10 Tesla is enormous, but an electric field of 10 volt per meter is tiny. It's even less than produced by a AA battery. Therefore, you can recognize that you're going to need to multiply the B by the large number speed of light in order to get E. This expression would apply whether we considered peak values or RMS values, and since we're dealing with RMSs, we're going to apply it to the RMS electric field and magnetic field so that we can then solve easily for the RMS magnetic field by simply dividing the previous result by the speed of light. And the answer we get is 2.58 times 10 to the minus 6 Tesla. And that concludes our discussion of the electromagnetic waves produced by a typical laser pointer.